This is example 8-3, dimensional analysis of a boundary layer. So we have a plate down here, water is flowing on it, and then as the water is flowing across it, it creates the boundary layer down here, right? Above the boundary layer, we get uniform flow. And now the question is, how do we find out what this height delta is right here? And we're given that we found through experiments that it depends on the distance from the start of the plate, which is x, the overall stream velocity once it becomes uniform, far enough away from the plate, and also the density and viscosity of the fluid. And so now we're asked to find out what the relationship is between the height delta and all these other parameters. And we're told to take delta and mu as the non-repeating variables. So we can start out by saying, just writing down our variables, right? So we have f of, what do we have? We have delta, we have x right there, we have capital U, and then we have rho, and we have mu. So that means how many variables? 1, 2, 3, 4, 5. So 5 variables, which means that in the context of Buckingham pi theorem, right, this would be n is equal to 5. All right, so now we need to find what m is, right? That's how many of the primary dimensions are here, MLT in our case, right? So let's write each of these in terms of MLT. We'll start with delta. Delta is a length and nothing else, right? Delta is L. X, same thing, also a length. U is a velocity, right? So that would be length over time. Rho is our density, right? That was mass per volume, so m L to the minus 3. And then lastly we have mu, which is the viscosity, is mass times length to the minus 1, t to the minus 1. That means we have all three of our primary variable dimensions, right? So we have 3 primary dimensions, which means m is equal to 3. Okay, now that I have m and n, we can find the number of terms that we need. So we'll have n minus m, that'd be 5 minus 3. That means we have 2 pi terms. All right, so we'll have to set up 2. Now we're already given that we're supposed to use delta and mu as the 2 non-repeating ones. So we can jump right in and do that. We can say start with delta. All right, then we can say that our pi 1 is in the remaining variables, so x to the a, u to the b, and rho to the c, and then times delta. What is that with regards to our dimensions, right? That's L to the a, then L t minus 1, that's our flow velocity, raised b. Our density was mass per volume, that'd be c, and then we're left with delta, which is a length, not raised to any power. If we write that down, right, then what do we get? Let's stay with the order of MLT, so we'll start with M. How many times does M show up? Only here. has an exponent of 1, so m is raised to c. L comes up in A, comes up in B, so plus B. How about here? It's C as well. Oh, but L is minus 3, so we have to do minus 3C is looking for at M there for a second. And then L to the first power, so just plus 1. And then for T, let's see, we have minus B. And that's it. Well, I already easily see that M and T have to be 0, but let's write it down formally. So we can say from that we get, for M, we get the equation 0 is equal to C. For L, we get the equation 0 is equal to A plus B minus 3C plus 1. And for T, we get the equation 0 is minus B. All right, 3 equations, 3 unknowns. So we can say based on this, we get, of course, that C is equal to 0 from our first equation. From our third equation, we get that B is also equal to 0. And then from our middle equation, we can solve that for A. So we can say A is equal to, that'd be minus B plus 3C minus 1. B and C are 0, so minus 1. That means my pi 1 is then going to be, if we go back up here, we had x to the A was minus 1. We had u to the b, u was 0. And then we had rho to the c, c is also 0, times delta. So those two fall out, so we just have delta over x. That'd be our pi 1 term. Then we can go to our second one, basically the same thing, but now instead of having delta, we'll use mu. So we can say with mu, right, we get our pi 2 term. And that would be same as before, x to the a, u to the b, and rho to the c, but now times mu. And that means from for our dimensions, x is just the length, u is length per time, and rho was a mass per volume, and then mu is given as mass per length per time. All right, same thing here. We'll start with m. So we have m shows up as c and as 1. C plus 1. Then L shows up at A, shows up as B, shows up as minus 3C, right, because it's raised to the minus 3. And then L is also shows up here as minus 1. And then T shows up as B, and then as minus 1 back here. So one thing that you can already see, right, of course, is that the kind of the variable terms are always going to be the same, right? Because like this set, we're not changing the set, we're just changing the last one. So my A, B, and C's are going to stay the same. It's just that whatever kind of the actual numbers are is going to change. So what do we see? So we get from that, we get, just like before, we get a equation for m. In this case, 0 is c plus 1. for L, we get 0 is 2 plus B minus 3C minus 1. And then for T, we get 0 is equal to B minus 1. Right? These zeros, of course, are because my pi term is supposed to be dimensionless. All right, what can we see from that? Well, we can see from that that C is equal to minus 1. We can say B is equal to 1 I have here. Where am I going? Let's double check with B. I have something else here. T, oh, this is a minus T here, so it should be a minus there. So that should be minus 1. All right. So that's then B is equal to minus 1. And then to get A, we can say that would be minus B plus 3C minus 1. And that would then B was minus 1, so it's plus 1. 1 minus 3 is minus 2. Minus another one is, I'm getting some other values. Let me double check on my equation here. We have A for time, for length, right? So we have A. We have not plus B, we have minus B. That's where we're going wrong. It's my eraser. That should be a minus. So let's double check it. L. No, it was a plus. I'm starting to confuse myself here. Is a plus? Looking at L, not at T. That's a minus 3. And then that's a minus 1. That all looks good. So now if I solve this for A, I had minus B plus 3C. Well, that was a minus 1, so a plus 1. There's that was the issue. So now we have B was minus 1, so that's a plus 1. Plus 1 minus 3 is minus 2, plus 1 is minus 1. There we go. That's what we're looking for. So that means pi 2 is then x to the a, minus 1, u to the b, which is minus 1 as well, and then c to the minus 1. All that, of course, times mu. So that means I get u divided by x times u times rho. And that means 1 over the Reynolds number. Okay, so that means we can say f of my 2 pi's, right? So it would be delta over x, comma, 1 over the Reynolds number is equal to 0. And then I can start solving that. I can say delta over x is equal to some other function. It's called f1. 1 over the Reynolds number. Of course, if I can have it of 1 over the Reynolds number, I can also rewrite that with a new function and say call that just the Reynolds number. Right, because we don't know what this functionality of what this function is, right? So right now we're just calling it an arbitrary function. And then if I solve that just for delta, then I have x times f2 times re. If I wanted to find out what my function is of this Reynolds number, then I would have to make experiments. But this is what we're looking for, right? So we found that if we want to find what this value x is, what this distance is, or what if we want to know that what this delta is, I'm sorry, right? Then if we know the Reynolds number and we know this distance from where this plate starts, then we should be able to find what delta is. We just have to figure out what this function is.